Now that we've learned a little bit of chemistry, we can put that knowledge to work and turn our attention to organic chemistry, the study of carbon-containing compounds. The key lesson to keep in mind from our study of chemistry is that an atom's chemical reactivity is determined by its electron configuration. This video is what the title suggests, an introduction to organic chemistry. We don't go deep into organic chemistry, we're just learning some basics that are going to get us through the course. Before I even start talking about organic chemistry, perhaps we should define what an organic compound is. For this class, an organic compound is any compound that has at least one carbon and at least one hydrogen. So, methane, CH4, is an organic compound. Carbon dioxide, CO2, is not an organic compound because it doesn't have any hydrogen. Okay, so one of the first questions we might ask is, why carbon, or what's so special about carbon? The answer to these questions comes really from the periodic table. So let's take a quick look again at the periodic table, and let's focus on these top three rows. Remember that as biologists, we're mostly interested in the top three rows because that's where all the action is in terms of biology. Note that this carbon atom occupies more or less a central position in that second row. That is, it is the fourth of 8 elements in the second row. There's 8 elements in the second row because the second shell can hold up to 8 electrons, and carbon has 4 electrons. That is, it's tetravalent. So carbon is in the middle. It's also in the middle in terms of electronegativity. So if we look to the right, we see elements like nitrogen, oxygen, fluorine, chlorine. Those are all elements with very high electronegativity. If we look to the extreme left, we see elements with very low electronegativity, sodium, magnesium, potassium. Carbon, however, and importantly hydrogen, are in the middle in terms of electronegativity. So that basically means that carbon is going to form stable covalent bonds. Okay, so if the question is why carbon or what's so special about carbon, the first answer should be that carbon forms stable covalent bonds with lots of different elements, but especially with hydrogen, oxygen, and nitrogen. The other thing that's special about carbon is the fact that it forms 4 bonds. I said a moment ago that it's tetravalent. That means it has 4 electrons in its valence shell. And of course that second shell is most stable when it has 8 electrons. Therefore, carbon forms 4 bonds. And its ability to form 4 bonds makes possible a great diversity of structures. And the last thing we should think about or keep in mind is the fact that carbon is relatively abundant on the Earth's surface. So just as an aside, where does all the carbon that's on Earth come from? The answer is that carbon formed in the earliest stars in our universe. Those stars would explode eventually and send their elements throughout the universe, and those exploding stars form new stars and new planets with the carbon incorporated into them. So that's where all the carbon in our Earth comes from a star that exploded billions of years ago. Okay, back to carbon and structural diversity. All right, so what we really want to do now is tackle this idea of chemical diversity or structural diversity of organic compounds. To take on the structural diversity of organic compounds, we're going to start with the simplest case, and that is hydrocarbons. As the name implies, hydrocarbons are compounds that contain just carbon and just hydrogen. And you're already quite familiar with hydrocarbons. An example is methane or ethane. Methane and ethane make up natural gas that we use to cook our food, heat our homes, or power electricity generating plants. Another example of a hydrocarbon is octane, which is the major component in gasoline. Okay, so by now you might think that these hydrocarbons release a lot of energy when they're oxidized. That is indeed the case, and that's going to come into play in a big way later on in the course. But let's return to the structural diversity of hydrocarbons. So they have a relatively simple chemical composition, yet they can form an enormous diversity of chemical structures. And the reason they can form such a diversity of chemical structures is that they can vary in terms of chain length, that is the number of carbons that make up the compound. they can have different branching structures. So two compounds with the same chemical formula can be different because of the branching of the hydrocarbon chain. Hydrocarbons can also form ring structures, which will increase their structural diversity. And while we're going to start off talking about single bonds, carbon can also form double bonds, which once again will increase structural diversity. Carbon also forms triple bonds, but we're not really going to deal with triple bonds here today. We'll start off talking about the simplest compounds, and the simplest compounds have carbon single bonds. And when carbon forms a single bond, it takes on a tetrahedral geometry. Let's take the simplest case, methane, CH4. So in this case, carbon forms a tetrahedron. So carbon is at the middle of this tetrahedron. A tetrahedron is a four-sided figure in which each of the sides is a triangle. Carbon occupies the middle of that tetrahedron, and the four hydrogens each make up a point of the tetrahedron. So that's shown here. It's shown here again without the lines drawn in. This is a little bit more accurate of a depiction. But you can see the tetrahedral shape. Now these drawings, these illustrations are very nice. If you happen to have a graphics art department drawing chemical structures for you, they come in quite handy. For the rest of us, we're probably going to draw structures to look something like this. Or we could draw it like this. This captures a little bit that tetrahedral configuration. Of course, we also have the option of just saying methane or writing down CH4. We're going to learn that writing down CH4 or just a chemical formula is not enough because sometimes that chemical formula can be ambiguous. So that's the simplest case, methane. Let's look at a slightly more complicated case, ethane. Ethane now has two carbons, C2H6. Once again, the tetrahedral structure is maintained. Note that this carbon is at the middle of a tetrahedron, and three of the points of the tetrahedron are occupied by hydrogen. The fourth point is occupied by a neighboring carbon. Now, with respect to this carbon, it is also at the center of the tetrahedron. Three of the points of the tetrahedron are occupied by hydrogen, and the fourth point is occupied by the neighboring carbon. So this is true. So carbon maintains the tetrahedral structure. That's true for one carbon, two carbons, three carbons, and that's going to be true for however many carbons we add, so long as we're dealing with carbon single bonds. Now, something interesting happens when we go to butane. Butane is a four-carbon molecule. Note that here's an example of butane, C4H10. Here it is drawn in a linear array. Here it is once again drawn in a linear array. This time we're trying to capture a little bit that tetrahedral geometry. Here it is drawn in a different way. In this case, we have, instead of having a four-carbon chain, now we have a 1, 2, 3 carbon chain, and we have a fourth carbon stuck onto that middle carbon. All right, so these two molecules have the same chemical formula, C4H10, but they are two different structures. They are two different molecules with different chemical and physical properties. This one is isobutane, and this one is butane. They are going to differ in terms of boiling point, in terms of solubility, and various other physical properties. So when two compounds have the same molecular formula, but different structures, we call them isomers. In this case, they're structural isomers. Another example of structural isomers are propanol and isopropanol. So here we have three carbons with an OH added to that third carbon. In this case, we have the same chemical formula, C3H7O, but in this case, the OH is added onto a central carbon. This is isopropanol, this is propanol. Once again, these are distinct molecules, each with its own physical and chemical properties. So let's go on from there. Butane has two possible structures, butane and isobutane. If we add a fifth carbon, now we're dealing with pentane, and pentane has three possible structures. I'm not going to go through them in detail, but you can look at them. You can pause the video and look at them yourself and show that and convince yourself that they are indeed three distinct structures. Now, if we go to hexane, with hexane, which is a six-carbon molecule, C6H14, 5 different chemical structures are possible. 1, 2, 3, 4, 5. Once again, I'm going to leave it to you to convince yourself that these are 5 different structures. And things get more complicated from there. Heptane, which is a 7-carbon molecule, can form 9 different isomers. And octane, an 8-carbon molecule, which we mentioned before, is a component of gasoline. can form 18 different isomers. All right, to make things more complex still, hydrocarbons can form ring structures. All right, here are two examples of ring structures containing 6 carbons: cyclohexane and benzene. Each have 6 carbons, and each are distinct molecules. Note that cyclohexane and benzene are not isomers of one another, and they're not isomers of hexane because they have different chemical formulas. The next element of structural complexity that we'll consider is the carbon-carbon double bond. So the carbon-carbon double bond, shown here, takes on a planar geometry as opposed to the tetrahedral geometry of the carbon-carbon single bond. What that means is that carbon and its binding partners all lie in the same plane, or they form a flat surface. And this has important implications when it comes to the structures of organic compounds. For example, here we have a pair of double bonded carbons. Each of these carbons in turn is bound to another carbon, or you could say that each of these carbons is substituted. Okay, in this case, the substitutions about the double bond are both on the same side of that double bond. Remember, these all lie in a plane. So the substitutions can lie on the same side of the double bond. The substitutions could also be on the opposite side of the carbon-carbon double bond. So when the substitutions are on the same side of the double bond, it's called a cis double bond. When they're on opposite sides of the double bond, it's called a trans double bond. If you find that a little bit confusing, perhaps a real-world example will help. Here we see 2 examples of fatty acids. Now we're going to learn all about fatty acids in our next lesson. For now, suffice it to say that fatty acids are a component of the fat that we find in our diet. Fatty acids can be either unsaturated, that is no double bonds, or they can be saturated, that is no double bonds, or they can be unsaturated, that is one or more double bonds. This one, which has a double bond, is called oleic acid, and it is a major component of olive oil. Naturally occurring double bonds in fatty acids are cis double bonds. So this is a cis double bond. And you can see it has a certain effect on the shape of the molecule. It adds this kink to the chain of hydrocarbons. No doubt you've heard the term trans fatty acid or trans fats. Trans fats are artificial and don't naturally occur in foods, with of course a few exceptions. Trans fats are introduced by food manufacturers by chemical processing. Food producers like double bonds because it takes liquid fats, like vegetable oil, and makes them solid, which in turn makes them easier to store, easier to ship, and gives them a longer shelf life. All things you worry about if you're in the business of processing and selling food. Trans fats have been in the American food supply since the 1950s. Many years later, it became apparent that trans fats are bad for you. Trans fats in the diet increase the risk of heart disease, so they're dangerous to human health. Why they increase the risk of heart disease is a little more than I want to get into right now. Suffice it to say that they're bad for you. So bad, in fact, that they've been banned in the United States. As of mid-2018, it is illegal to sell foods that contain trans fats. Hopefully, this will make us all a little bit healthier. Okay, so let's do a little bit of review. Organic compounds, again, we're dealing with the simplest case of organic compounds, the hydrocarbons. They can have an enormous amount of structural diversity, and the reason they have that structural diversity, or the reason that one hydrocarbon differs from another hydrocarbon, is due to the chain length, the degree of branching, whether or not there's branching, and the degree of branching, whether or not there's ring structures, and whether or not there's double bonds. But things get more complicated from here because organic compounds contain more than just carbon and hydrogen. They contain other elements as well. Other elements that bind to carbon usually do so in groups. We call them functional groups. Functional groups are combinations of atoms which, when added to an organic compound, change the properties of that organic compound. Your book goes over, I think, 7 different functional groups. Here I've listed just 5 of them. Make things a little bit easier for you. I think these are the most important 5. We're going to go over each of these functional groups in detail in a few minutes. For now, let's just list them. Methyl hydroxyl OH, amino NH3, carboxyl, COOH, and phosphate, OPO3. Note that each one of them is preceded by this little dash. That dash basically represents a bond between this functional group and a carbon on a larger organic compound. Okay, so let's go through them one at a time. The simplest functional group is the methyl group, CH3. It is itself a simple hydrocarbon. And because it contains just carbon and hydrogen, it's a hydrophobic functional group. And when added to an organic compound, it will make that organic compound more hydrophobic or less water soluble. So here's an example of a methyl group added to a larger organic compound. This one is thymine. Adding the methyl group changes uracil into thymine. And that's going to take on a lot of meaning for us when we study the structure of DNA. The next simplest functional group that we'll consider is the hydroxyl group, OH. Because this one contains oxygen, this is a more polar functional group. So it makes the organic molecules that it's added to more polar, more hydrophilic, or more water soluble. And this is one you're familiar with. You're probably familiar with both of these compounds. This one is ethanol. Ethanol is a 2-carbon molecule with this hydroxyl group. If it didn't have that hydroxyl group, it would be ethane. With the hydroxyl group, it's ethanol. In fact, all alcohols have that hydroxyl group. Another name for the hydroxyl group is an alcohol group. Ethane, without the hydroxyl, is very different than ethanol. Ethane is a gas and it's not water soluble. Ethanol is a liquid and it's very water soluble. So the hydroxyl groups come into play when we talk about sugars. Glucose is an example of a sugar. And like all sugars, glucose has these multiple hydroxyl functional groups added. And that makes glucose very water soluble. And as we're going to see, all sugars are very water soluble. The next functional groups we'll actually take in a pair. We'll talk about the carboxyl group and the amino group. Carboxyl group, which I like to call carboxylic acid group, others will call it just an acid, is this here, C double bond O bond OH. As the name implies, it is acidic. And acidic means that this group right here, here's the functional group, it's acidic because it gives up this proton. When it gives up this proton, it takes on a negative charge. And because it takes on that negative charge, it makes compounds that it's added to ionic. It's ionic because this is charged. And when a compound is charged like this, it becomes very water soluble. So this is a very water soluble compound. Compounds that have a carboxylic acid group attached to them become more water soluble. At the other end of the pH scale are bases. So NH2 is an example of a basic functional group. So here's NH2 attached to an organic compound. Because NH2 is a base, it will take on this additional proton. It takes on an additional proton and becomes positively charged. Once again, because this is charged, it becomes more water soluble. All right, so now that we've covered carboxylic acid and amino groups, we can talk about this another very special compound, the amino acid. Amino acids are the building blocks of proteins. So we're going to spend a lot of time on amino acids when we get to the protein lecture. For now, let's just take a quick look at their structure. As the name implies, an amino acid has both an amino group and a carboxylic acid group. Now you see why I like to call it an acid. So all amino acids have the same structure. That is, this central carbon bound to an amino group, bound to a carboxylic acid group, bound to a hydrogen, but then its fourth substitution can be variable. Okay, that's what that R stands for, some variable functional group. Or we can call it a side chain. So all amino acids are the same except for their side chain. And it is the identity of this side chain that's going to determine the properties of the protein in which these amino acids are incorporated. Okay, so that leaves just one more functional group, the phosphate group. Phosphate group, as you can see, is very negative. OPO3 2 negative, so that's going to impart a lot of negative charge. Here's an example of an organic compound with a phosphate group on it, and because this has this double negative charge, this is going to be very water soluble. So the phosphate group is going to come into play over and over again this semester. We're going to learn about it in the next lecture when we talk about phospholipids. We're going to learn a lot about it when we talk about the structure of DNA. because it has a sugar phosphate backbone. But we're also going to learn a lot about phosphates because of this molecule right here, adenosine triphosphate, or ATP for short. As the name implies, it has 3 phosphate groups, 1, 2, 3. And this is a very important molecule because these phosphate groups carry a lot of energy. So when we split off this last phosphate, that is, break the bond between phosphates 2 and 3, we release a lot of energy. The energy that we release is going to be used to power a lot of reactions in biology. In fact, the next couple of weeks is going to be spent learning a lot about the reactions that are powered by ATP, and we're also going to learn about how the cell makes ATP. Okay, now that we've learned something about organic compounds and their structural diversity, in the next lesson we'll apply this knowledge to large biological molecules.